Dear students, today we'll see some multiple choice questions on filters. So let's start with the today's main topic. So it is DCET or Communication Systems Part 5, in which we'll see some multiple choice questions on specifically passive filters. So we'll start with the questions on filters. So let's start with the first question. Question number 81. What is a filter? Now in electronic studies, whenever we study analog electronics, the filters are different, and whenever we study our communication subjects, the filters are different. Now as per the our communication subject, if a question is asked what is a filter, then it is a circuit which will pass certain frequencies, which will pass desired frequencies, and will block unwanted frequencies, or it will ignore or it will reject the unwanted frequencies. So based on frequency, we are going to have filtering action, and that is why it will be called as a frequency selective circuit. So here, out of these four options, the first option, option A, that is frequency selective circuit, is the correct answer. So what is a filter? A filter is a frequency selective circuit. So if you see the explanation behind it, a filter is a frequency selective circuit. Filters are designed to pass some frequencies and reject others. Filters are used to reduce noise and increase selectivity. So here the option A will be the right answer, that is frequency selective circuit. Then we'll go to the next question. What are filters created by using resistors and capacitors, or inductors and capacitors? Now we know these are components like resistors, inductors, and a capacitor. If you see resistors, inductors, and capacitors, now these are components which come under classification of passive devices. These all are passive devices, and therefore the filters which are built by these passive devices are called as passive filters. So here option B will be the right answer, that is passive filters, because these filters include a combination of inductor resistor, resistor capacitor, or a capacitor inductor. Okay. So here we can have this explanation. Some filters created by using resistors and capacitors, or inductors and capacitors, are passive filters because they use passive components that do not amplify. In our communication work, many filters are of the passive LC variety, although many other types are also used. Okay. So here the option B is the right answer. The filters which are created by resistors, capacitors, and inductors are called as passive filters. Then we'll go to the next question. What type of filter produces a predictable phase shift characteristics in all frequencies? Okay. Now the filter which will pass all frequencies is called as all pass filter. Now it is going to pass all frequencies, but it will be having a predictable phase shift problem in it. Okay. So the filter which produces a predictable phase shift characteristics in all frequencies is all pass filter. So here option D will be the right answer, that is all pass filter. So here we can have explanation here. An all pass filter passes all frequencies equally well over its design range, but has a fixed or predictable phase shift characteristics. Filters normally attenuate the signal applied for some values of frequency, whereas on all pass filter retains the signal level at all frequencies. So here this filter is going to pass all frequencies, but it has a fixed or predictable phase shift characteristics. So here all pass filter is the right answer. So here you can see option D, that is all pass filter, is the answer for which type of filter produces a predictable phase shift characteristics in all frequencies. Then we'll go to the next question, question number 84. An RC coupling circuit is an example of what type of filter? Now if you see the combination of RC coupling circuit, okay, so the coupling will be in series with a capacitor, and then we have a resistance here where the voltage is developed, and then you are going to get output here. Okay, so this is the input. So this is your RC coupling. RC coupling. Now here, if you put this capacitor in series, that means the reactance of capacitance, which is given as Xc, is equal to 1 by 2 pi Fc. Okay. Now if frequency is high, the reactance is less. That means this is going to pass high frequencies. This is going to pass high frequencies to the output. Clear? Now this high frequency is going to the output will give you a filter which has the characteristics of high pass. So high pass filter will be the right answer here, because the voltage developed across R will be the output voltage, but the frequency which is going to come out because of the capacitor in series is going to give you the characteristics of high pass filter, because reactance for low frequencies will be more provided by the capacitor. So low frequencies will be blocked and high frequencies will be passed. So it is going to act as high pass filter. So here we will see the theory behind it. An RC coupling circuit is an example of a high pass filter because the AC component of the input voltage is developed across R and the DC voltage is blocked by the series capacitor. Furthermore, with higher frequencies in the AC component, more AC voltage is coupled. So therefore, option B is the right answer. RC coupling circuit behaves as a high pass filter. Then we'll go to the next question. What is the type of filter shown in the figure? In the figure, we see that there is a resistance here which is in series, and there is a capacitor which is in parallel. That means if you give the combination of frequencies here, the frequencies will pass here. Now high pass frequencies will go to the ground because there is a capacitor here, and the reactance, that is opposition to the flow, we are given by the capacitor. Xc is equal to 1 by 2 pi Fc. So it is less for high frequency. So all the high frequencies will go to the ground, and what goes at the output will be your low frequency. Low frequency. Therefore, the type of filter shown in the figure is low pass filter. So it is going to pass all the frequencies which are in the lower range. So option A is the right answer here, low pass filter. So here you can see explanation for that. The simplest form of low pass filter is the RC circuit shown in the figure. The circuit forms a simple voltage divider with one frequency sensitive component, in this case the capacitor. At very low frequencies, the capacitor has very high reactance compared to the resistance, and therefore the attenuation is minimum, thus allowing lower frequencies to pass through while attenuating higher frequency signals. Therefore, it is going to act as low pass filter. So here option A is the right answer. The figure which shown will act as low pass filter. Then we'll go to the next question. Find the cutoff frequency of an RC low pass filter of R is equal to 8.2 kilo ohms and C is equal to 0.0033 microfarad. So here, if you see the formula for a cutoff frequency in low pass filter, so the formula will be for a cutoff frequency, it will be 1 upon 2 pi RC. Now we are taking here R and C elements to build up this filter. Now if you substitute the values of this, we'll get cutoff frequency is equal to 1 upon 2 into 3.14 into R is 8.2 into 10 to the power of 3 because it is 8.2 kilo ohm, and C is 0.0033 microfarad, so it is into 10 to the power of -6. So if you solve this, FCO will get as 5.88 kilohertz. It will be 5.88 kilohertz, and here the option B will be the right answer here, 5.88 kilohertz. So the cutoff frequency formula for low pass filter is 1 upon 2 pi RC, and if you substitute the values given in the numerical, so R is equal to 8.2 kilo ohms and C is equal to 0.0033 microfarad. If you substitute them, we'll get cutoff frequency is equal to 5.88 kilohertz. So here you can see the solving, and in this solving we get 5.88 kilohertz as the answer, and therefore option B is the right answer here, that is 5.88 kilohertz. Then we'll go to the next question, question number 87. What is the type of filter shown in the figure? In this figure we see a filter which is having inductor in series and a resistance in parallel. So the inductor in series will pass all the low frequencies, and therefore the filter here shown will act as a low pass filter, because the reactance provided by inductor XL is equal to 2 pi FL, and therefore if the frequency is low, reactance is low, therefore lower frequencies will be passed. So you are going to pass here low frequencies, and therefore because you are able to pass low frequencies, it is going to be a low pass filter, and it is going to block high frequencies, because as the frequency increases, reactance of the inductor increases, and therefore it is going to pass only the low frequencies, and therefore it is going to act as low pass filter. So option A is the right answer here, low pass filter. So here we can have an explanation. A low pass filter can also be implemented with an inductor and a resistor. Inductor allows lower frequencies to pass through while attenuates higher frequency signals, and therefore this combination acts as low pass filter. So here option A, that is low pass filter, will be the right answer. Then we'll go to the next question, question number 88. What is the value of resistor for a high pass RC filter to produce a cutoff frequency of 3.4 kilohertz, and if C is equal to 0.047 microfarad? Now, if we start this example, we should know the formula of cutoff frequency. So, cutoff frequency for high pass filter is also given as 1 upon 2 pi RC. Okay, now here we have FC as 3.4 kilohertz. Now we have to find out what is R. So if you want to find out what is R, then R will be equal to 1 upon 2 pi FC into C. So this is nothing but 1 upon 2 into 3.14 into FC is how much? 3.4 kilohertz. So it is 3.4 into 10 to the power of 3, and C is how much? 0.047 microfarad. So it is 0.047 into 10 to the power of minus 6. Now this is what is given, and with this calculation we find out R is equal to 996 ohms. So option C will be the right answer here. It is 996 ohms. So here you can see the calculations. With the same calculations we have done, and the answer here what we get is 996 ohms. So here you can see option C, that is 996 ohms, is the correct answer. Then we'll go to the next question, question number 89. Notch filters and band reject filters are the same. Is the statement true or false? Yeah, band reject filters is one which is going to reject a particular band of frequency. Many a times we can choose a narrow band of frequency will be rejected, and a notch filter also is going to do the same thing. It is going to reject a particular frequency. So notch filters and band reject filters characteristics are same, so this statement is true. So option A is the right answer here. So here we can have explanation for that. Notch filters are also referred to as band stop or band reject filters. Band reject filters are used to greatly attenuate a narrow range of frequencies around a center point. Notch filter accomplish the same purpose but for a single frequency. Therefore, notch filters and band reject filters have the same characteristics. Okay, so here option A is correct, because notch filters and band reject filters are going to behave the same. So option A, that is true, this statement is true. Then we'll go to the next question, question number 90. What is the value of notch frequency if the values of resistance and capacitance are 100 kilo ohms and 0.02 microfarad? Now here the expression for notch frequency will be the expression for cutoff frequency. So that is 1 upon 2 pi RC. So if you substitute the values, it is 1 upon 2 into 3.14 into R is 100 kilo ohms. So it is 100 into 10 to the power of 3, and C is 0.02 microfarad. It is 0.02 into 10 to the power of minus 6. Now this, if you substitute and simplify, we'll get notch frequency is equal to 79.6 Hertz. So here option A will be the right answer, 79.6 Hertz. So here you can see this calculation will give you 79.6 Hertz. So here option A is the right answer, that is 79.6 Hertz. Then we'll go to the next question. What is the loss the filter introduces to the signals in the pass band called as? Now, whenever we insert a filter, okay, the loss the filter introduces to the signals in pass band is called as insertion loss. So here option B is the right answer, that is insertion loss. So here we'll have the theory behind it. Insertion loss is the loss the filter introduced to the signals in the pass band. Passive filters introduce attenuation because of the resistive losses in the components. Insertion loss is typically given in decibels. So here option B, that is insertion loss, is the right answer. Then we'll go to the next question. The attenuation rate is also called as, okay, now whenever we see attenuation rate, say for example if you are having a graph of low pass filter, so this is gain, and if this is frequency and this is 0, so if you have a graph, so the graph will show it like this. So here this is your attenuation rate, this is the attenuation rate. Or if you see a high pass filter, okay, so high pass filter will have the same thing but with the opposite side, that is if you are having gain and frequency here, so gain here and frequency here. Okay, so here you can see attenuation will be like this, and then you're going to have this. Okay, so this is pass band and this is stop band. So here in low pass filter, this is pass band and this is stop band. So in low pass filter, we can definitely see and tell it specifically that this coming down graph, this graph which is dropping from the pass band gain towards a minimum value in the stop band, this is called as attenuation rate, and this is nothing but roll off. It is rolling off, so it will be having a rate of rolling off like 20 decibels per decade, and it is termed as roll off. So option A is the right answer here, which is called as roll off. So here we can see explanation. Roll off is also called the attenuation rate. Roll off is the rate of change of amplitude with frequency in a filter. The faster the roll off or the higher the attenuation rate, the more selective the filter is, that is better able it is to differentiate between two closely spaced signals, one desired and other not. Okay, so it is called as roll off. So here option A is the right answer, that is roll off. The attenuation rate in a filter is also called as roll off. Then we'll go to the next question. An RL high pass filter consists of 470 ohms resistor and 600 microhenries coil. The output is taken across the coil. The circuit's cutoff frequency is how much? Now here again we have to start with the formula for the cutoff frequency, and the cutoff frequency formula says that we have a cutoff frequency FCO is equal to 1 upon 2 pi RL. Now here this is the cutoff frequency in case of RL high pass filter. So here if you substitute the values, 1 upon 2 into 3.14 into R is how much? 470 ohms, and L is how much? 600 microhenries. So it is 600 into 10 to the power of minus 6, and this answer is nothing but, if you substitute all these values, so this if you simplify you will get 0.564 Hertz. So here option C will be the right answer, that is 0.564 Hertz. So here you can see for this numerical example, option C is the right answer, that is the cutoff frequency is 0.564 Hertz. Then we'll go to the next question. An RC low pass filter consists of 120 ohm resistor and a 0.002 microfarad capacitor. The output is taken across the capacitor. The circuit's critical frequency is dash. Okay, now here if you see, again we are going to use the same formula. So the cutoff frequency here for this RC filter is nothing but 1 upon 2 pi RC. If you substitute them, it will be 1 upon 2 into 3.14 into R is 120 into C is nothing but 0.002 microfarad, so it is 10 raised to minus 6. If you substitute all these values, we'll get cutoff frequency as 663 kilohertz. So here option B will be the right answer, that is 663 kilohertz. So here you can see for this numerical example, option B is the right answer, that is 663 kilohertz. Next, we'll go to the next question. In a certain low pass filter, the cutoff frequency is 3.5 kilohertz. So its pass band is how much? So if its a cutoff frequency is 3.0 kilohertz, that means it is going to pass frequencies from 0 to 3.5 kilohertz. So its pass band will be 0 hertz to 3.5 kilohertz. So here option A will be the right answer, that is 0 hertz to 3.5 kilohertz. So here you can see option A is the right answer. Then we'll go to the next question. The maximum output voltage of a certain low pass filter is 15 volt. So here we have maximum voltage is equal to 15 volt. The output voltage at critical frequency is given as how much? So the output voltage at a critical frequency is given as Vm upon root 2, and this is nothing but 15 upon root 2, and this is nothing but 10.60 volt. So here option A is the right answer, that is 10.60 volt. So here you can see option A, 10.60 volt is the correct answer. Then we'll go to the next question. At a certain frequency, the output voltage of a filter is 6 volt and the input voltage is 12 volt. The voltage ratio in decibels is given as. Now if you see the voltage ratio in a decibels, that is the voltage gain in a decibels. Okay, in decibels, it is given as 20 log V out upon V in. So this is nothing but 20 log, how much is V out? So here the output voltage is 6 volt and the input voltage is 12 volt. So it is 6 upon 12. Okay, so it is nothing but 20 log 6 upon 12 is we have 6 1 the 6 6 to the 12, so it is 0.5. So 0.5, and this if you take log of 0.5 and multiply by 20, we'll get this answer as minus 6.02. So it is minus 6.02 decibels. So here option B will be the right answer, that is minus 6.02 decibels is the right answer. So here you can see minus 6.02 is the right answer. Then we'll go to the next question. Question number 98. In a certain parallel resonant band pass filter, the resonant frequency is 14 kilohertz, and if the bandwidth is 4 kilohertz, what is the lower frequency? So if you see the graph over here, so if you draw the graph for this band pass filter, it will be gain versus frequency. This is 0. So we'll be having a cutoff frequency. So it is a band pass filter, so we'll be having two cutoff frequencies. This is 1 and then this is 1. Okay, now here in this question it is given that the bandwidth is 4 kilohertz. So this is the bandwidth, this will be 4 kilohertz. Okay, so that is F2 F1. And now if the lower frequency, we have to find out if the resonant frequency is 14 kilohertz, if the center frequency is 14 kilohertz, then it will be 14 kilohertz minus 2 kilohertz here, and it will be 14 kilohertz plus 2 kilohertz here. So if we want to find this lower frequency, it will be 14 kilohertz minus 2 kilohertz, which will be nothing but 12 kilohertz. So here option C will be the right answer. The lower frequencies are on 12 kilohertz. So here you can see option C is the right answer. Then we'll go to the next question. The filter that passes high frequencies and rejects low frequencies is called as. This is a very simple question. So the filter which passes high frequencies and rejects low frequencies is called as high pass filter. So it is option A which is the correct answer, that is high pass filter. Then we'll go to the next question, question number 100. Filters are classified as analog or digital filters, passive or active filters, audio or radio frequency filters. So all these three are true because filters can be classified as analog filters or digital filters. They can be classified based on the components as passive filters or active filters. They can be classified on the based on the frequencies as audio frequency filters or radio frequency filters, that is AF filters or RF filters. So all of the above mentioned are true. So filters can be classified by as all of the above three statements. So option D is the right answer here, all of the above mentioned. So here we can see option D is the right answer. Thank you, students.